In this video, we are going to discuss the recently patented hybrid sand filtration system known as EcoWash. Sand filtration has been around since the beginning of water treatment. There is evidence of sand filters dating up to 4,000 years in the past. This predates the famous Roman aqueducts. Why these filters have been around so long is simple. Quite literally, it is their inherent simplicity. Create a vessel for sand, pour water through it, and you have a sand filter. The big stuff stays in, the small stuff comes out. As an example, say you are stranded on a deserted island and need to clean water for drinking. You could create a sand filter quite easily by using something like a bucket, assuming one happened to wash ashore with you. Make some holes in the bottom, and voila, you have a sand filter. As you pour water through your sand filter, solids will get stuck in the sand bed, while the water, minus the solids, will come out the bottom. As this operation occurs, the solids that build up in the bed, known as a Schmutzdecke, will cause two things to occur. The first is, the solids in the bed will begin to aid in the filtration process, causing the effluent water to be cleaner as time goes on. It would be great if this process went on like this indefinitely, but as mentioned, there is a second effect, and that is the pressure needed to push the water through the sand bed will also increase. Eventually, the pressure will reach a point where that process can no longer continue. In our bucket example, it is when the water level in the bucket would exceed the freeboard height available and overtop. This is the point where the filter will need to be taken offline and cleaned. Once cleaned, the pressure will return to normal, and so will the effluent TSS. This process continues through the use of the filter. This filter, however, is inherently smart. If you pour clean water into the bucket, it will go longer between needed cleanings. If you pour dirty water into the bucket, it will require cleaning more often. This simple bucket will actually dictate the optimal time to clean that will maximize the solids buildup and effluent TSS depending on the inlet water quality. This is because this filter operates based on solids. This is how traditional gravity filters have operated for thousands of years. Being based upon solids, they are inherently smart, but they come with their drawbacks as well. In our deserted island example, the need to take the filters offline to backwash was not an issue. However, in treatment plants and full-scale facilities with continuous flow, we now have the need for redundancy. We now need twice the filters for normal operation. Where there was a need for one, for example, there is actually a need for two for normal operation, because one will be backwashing while the other is operating, and vice versa. If there is then a need for true redundancy, you actually now need three. So there are two for normal operation, plus an extra in case one goes down. In addition, you will need backwashing tanks, pumps, valves, controls, and many other ancillary pieces of equipment to make these operate properly. Due to these shortfalls, the continuous sand filter was designed and introduced into the marketplace a little over 30 years ago. These filters work by continuously, hence the name, taking sand from the filter, cleaning it, and then returning it to the top of the sand filter again. This process occurs while the system is in operation, and therefore there is no need for redundancy. As with traditional filters, however, there is a catch. The continuous filter runs based upon hydraulics, not solids. So it lost the smart the traditional filter had. The effluent and pressure are maintained constant, regardless of influent solids concentration, and since changes are not automated, the initial settings need to be for a worst-case scenario. Therefore, the filter is always running over what is necessary. This leads to excessive backwash and underachieving effluent. And this is where our industry remained for over 30 years. A constant give-or-take decision had to be made for each installation as to what was most important: the smaller, simpler, continuous filter that is based upon hydraulics, or the larger, bulkier, more complex system based upon solids. It didn't take long for engineers to figure out that it would make the most sense to combine these two filters, i.e. use the body of the continuous filter, but the mind, the operational methods of the traditional. In other words, use a continuous filter, but run it based upon solids, not hydraulics. As with many things, this sounded much simpler than it actually was, as it took over 30 years to introduce, and Parkson Corporation was awarded a patent for its design. The reasons for this, and how the engineers at Parkson were able to overcome these obstacles, will come later. The DynaSand EcoWash hybrid filter utilizes the body of a continuous filter, but operates like a traditional filter based on solids, and therefore gets the best of both worlds. In order to go into detail of how this hybrid filter works, we need to first understand the inner workings of a continuous filter, which is a body that is utilized in the design of the hybrid. The following animation will review how the DynaSand continuous filter works, and as we walk through it, I will note when and how the filter would be operated in continuous mode versus as a hybrid. The DynaSand filter consists of an open sand bed, which houses modules which are utilized to both deliver water to the bottom of the sand bed and also take dirty sand from the bottom of the filter up to the top for cleaning. In this example, we see 4. Dirty water enters from an open top channel, which is on the upper right, and flows through a central pipe to each module. The filters are upflow, so the water is introduced at the bottom of the bed. The water fills up the bottom cone, however this area is not for water treatment. These cones are there to direct sand to a single point to be brought to the top of the filter for cleaning. The water for cleaning is distributed through the bed via feed radials, then moves upward as it is cleaned. As with our bucket example, the solids build up in the bed as the water passes through to the top and leaves via an effluent weir, as seen here on the upper left-hand side. If we pause here, the process is working exactly as a traditional filter. By operating simply as shown, the dirty water is fed through a static bed in which solids are being deposited. As time goes on, these solids will fill the gaps in the sand and catch smaller and smaller solids, resulting in cleaner and cleaner water. However, as this occurs, the pressure needed to push the water through the bed will also increase, to the point where the level in the influent channel, seen in the upper right, hits a value that we set as a maximum. At this point, we need to clean the sand bed. However, we are going to do it while the filter is still running, so that we don't have the redundancy, ancillary equipment, and complexity needs of a traditional gravity filter. If this were a continuous filter, however, the sand washing process would be occurring all the time, and this moment of soul filtration would not occur. Assuming we have reached a point in the process where we want to begin washing sand, we first need to take the dirty water and sand out of the system. This is done via a small amount of air sent to the bottom of the filter, where we have utilized the cones we spoke about earlier to bring the dirtiest sand to a single point for lifting. A small amount of air is introduced in a tube called an airlift, which then does what air does in water, and that is rises up through the tube to the top. This then creates a void, which the sand from outside the tube will fill, and when the next bubble of air is introduced, it will take this sand with it to the top. This process is repeated continuously, and this is how the sand and dirt are lifted to the top of the filter and out of the system. On the way up, the turbulence from the movement separates the dirt and solids from the sand. Once the dirt and sand have been brought to the top of the filter, we need to separate the two. The sand needs to be returned to the filter and the dirt taken away from the system. This is done via a sand washer, which is a green corrugated section seen here. The water flowing up this section is at a precise velocity that the sand can fall against it, but the dirt cannot, and thus we have our separation. The dirt is carried out of the system by this reject stream, and the sand falls against the flow and back onto the filter bed. This process continues until the sand bed is cleaned, and, if running as a hybrid, the filter goes back to the original filtration-only mode until dictated to clean again by the solids buildup. As noted earlier, the path to hybrid filtration was not an easy one, as there were some inherent obstacles that kept engineers from rolling out these systems for all these years. The first was monitoring. Since the method for lifting the sand is indirect and non-mechanical, when the system initially starts, the initiation of sand washing needs to be visually verified. This is not an issue on continuous filters, as they are not started and stopped often. But in a system like the hybrid filter, which would be turning on and off at all times during the day and night, you can't exactly have a staff member permanently situated up there. The monitoring method had some pretty strict requirements for success as well. It needed to be real-time and continuous, cost-effective, ensure sand washing had initiated, ensure proper sand washing throughout the cycle, and ensure reject valve closure during and throughout the off cycles. Monitoring all these items would get prohibitively expensive, with individual systems for each, so a single point needed to be found that could be monitored. The engineers at Parkson studied the hydraulic profile through the filter and found a pinch point at which, during any of the cycles mentioned here, a specific water height would indicate proper operation. Too high or too low of water level would indicate something was wrong, and therefore all the operational modes of sequence could be monitored at a single point with an inexpensive level sensor. The next obstacle to hybrid filtration were turbidity spikes. When first running the filters in hybrid mode, when the sand washing was first turned off, we saw what we expected, which was a drop in TSS. However, when the time came to turn the sand washing back on, instead of seeing the TSS level come back to the original point, it actually increased above that level before dropping again when the sand cleaning stopped. This spike in turbidity would take away a lot of the benefit of turning off the sand in the first place. If we zoom in on where the air is introduced at the bottom of the airlift, the cause for this becomes apparent. When air is introduced into a closed system, it expands and exerts a pressure within that system. Although we want this expansion in the air to only go up, nature doesn't work that way, and the expansion occurs in all directions, which includes up the airlift tube, but also exerts a pressure back on the sand bed. The pressure on the bed causes a slight jostle, which releases the smallest of the solids up through the top of the bed and into the clean filtrate, which causes a spike in turbidity. The engineers involved quickly realized they needed a soft start for the air introduction. By first introducing the air higher up in the airlift pipe, the force exerted by the air is completely contained within the pipe and away from the sand bed. Once this is done, the sand within the pipe is fluidized, and the air introduced at the bottom will expand in the path of least resistance, which is up, where we want it, leaving the sand bed alone. Now let's take a look at some real data. The full-scale testing of the EcoWash system was done at a water reuse facility in Pompano Beach, Florida. At this facility, filters running in continuous mode were run alongside filters running as hybrids with the EcoWash system. The blue line in the top graph shows the constant effluent turbidity produced by the continuous filter. The green line shows the effluent of the hybrid filter. We can see clearly here the sawtooth type graph that we had been drawing based on theory of operation up until now. We can also see the effect of the dual airburst soft start, as not only does the turbidity not exceed the baseline turbidity, but most of the time it never even gets close. Below this, you can see the pressure increase and drop associated with these changes as well. Here are some long-term results that show what the effect of the hybrid filter is over time. By allowing the filter to dictate optimal operation, we see significantly better results over the long term. Most affected by hydraulic versus solids-based controls are ENR systems, where the bed of the filter is utilized as an anoxic reactor to remove nitrates and nitrites. These systems require a carbon source, which is typically provided via methanol. Any overwashing or other inefficiencies quickly become apparent by an increase in required methanol over the stoichiometric requirement. Due to their inefficiencies, the amount of methanol typically required of continuous filters is greater than this stoichiometric amount. To find out if we truly created a hybrid filter, the EcoWash would need to match only the stoichiometric value like a traditional filter is able to do. At Laurel, Delaware, which is an ENR installation, data was collected on the amount of methanol needed for operation over the period of a year with a continuous filter. After this, the filters were upgraded to EcoWash hybrids and the methanol usage dropped. Over time, the methanol dose dropped to the stoichiometric value, thereby solidifying the result that a true hybrid filter had been created. Now that the filters are running on solids, we were able to see just how much more efficient hybrid filters are. By running as hybrids, reject water has typically been reduced by 90%. The same results were found for power requirements of the compressed air system, and all wear parts associated with the operation of the filters. The basic lesson learned in the development of this system is that in many cases, it is better to allow nature to dictate a process as much as possible. Instead of telling the filter when and how to operate, with the DynaSand EcoWash filter, we have taken a step back and allowed the filter to tell us how it needs to operate. You might say the DynaSand filter is as smart as a bucket of sand.